Students, in this session I take up again electrostatics revision but in a slightly different manner. Here I just go through a synopsis, along with that some examples will be solved this time. Say first we just start with charge properties. You all know charges are conserved. That means total charge of a system is always constant. Second one, charge is quantized. That means any charge can be written as integral multiple of electronic charge value, that is 1.6 10 raised to minus 16. And third property is charges are additive in nature. That means they get added algebraically. Let me write them one by one. So charge properties basically three. We can also say fourth one, like charges repel, unlike charges attract. But for the time being, we take three. First one, conserved. Second one, quantized. Third one, additive property. Now, conserved means total charge of the system remains constant. Quantized means any charge Q can be written as integral multiple of elementary charge E, or the charge on the electron without sign. We take 1.6 10 raised to minus 19 coulomb. And additive property means, say, charges get added algebraically. If you have 5 plus 5 coulomb minus 3 coulomb plus 8 coulomb, then if we club them together, we get 5 minus 3, 2 plus 8, 10 coulomb together plus. So this is what we call as additive property. These three are the properties. Now, to apply these things, we learn two numericals, two MCQs on this. We just learn them now. Observe carefully. First property, first question in the MCQ. Two identical spheres carrying charge of minus 9 microcoulomb and 5 microcoulomb respectively are kept in contact and then separated from each other. Point out true statement from the following in each sphere. Observe here, we read the question carefully. Two identical spheres carrying minus 9 microcoulomb, 5 microcoulomb are kept in contact. When they are kept in contact, charge redistribution takes place. That means additive property of the charges will come into way there. That means the net charge remains on both the spheres is minus 9 microcoulomb plus 5 microcoulomb, that is minus 4 microcoulomb only. And this minus 4 microcoulomb, as their identical spheres, get equally distributed on sphere 1, S1 we say. Half of this minus 2 microcoulomb, on sphere 2, half of this minus 2 microcoulomb will be distributed. And observe now, we read the next part there. In contact and then separated from each other. Point out the true statement from the following in each sphere. So we read the statements now. 1.25 10 raised to 13 electrons in deficit. That means we know whenever shortage of electrons is there, that object exhibits positive charge. And whenever excess of charge is there, that object exhibits negative charge. Here, S1 and S2 both have minus 2 microcoulomb. That means there is negative charge on both. That means there is excess of charges. Observe how we are analyzing this situation. So, there should be excess of electrons. By analyzing this idea, by additive property, we got total charge on both the conductors, both the spheres when we connect them. And once we remove them, total charge gets redistributed because their identical spheres, means their radius and everything remains same. And that is possible because once we connect them, they acquire same potential. Once they acquire same potential, as they are identical spheres, they must have same charge. That's why S1 and S2 are minus 2 microcoulomb. As they are negative charge, that means we know there is excess of electrons. Therefore, excess is one part of the answer. Now we read. So first option is not correct. Second, 1.25 10 raised to 13 electrons in excess. That means, say excess is okay. 1.25 10 raised to 13, how we are getting it? Say, that is number of electrons they are calculating. S1 and S2 have 2 microcoulombs. That means we have to calculate the number of electrons by using this. For that, we have to use quantization of charge. Q equals N into E. Observe, in this only one MCQ, we got all those ideas of the properties of the charges, except for charge conserved. Even that is also true, because once charge is conserved, because of the additive property, net charge minus 4 microcoulomb remains as it is. Oh, all the three properties are included in this problem. And Q equals N into E. So N equals Q by E, the number of free electrons. So N equals Q is 2 micro 10 raised to minus 6 by E, charge value 1.6 10 raised to minus 19, which amounts to be 1.25 10 raised to 13 electrons. So observe, with this value there is excess to be added. Therefore, second option is right. Second option B is right. We think of one more MCQ as an example of properties of the charge. We read the second one. A ball with charge of minus 50 E is placed at the center of a hollow spherical shell which has a net charge of minus 50 E. What is the charge on the shell's outer surface? Say here, not only additive property of the charge to be used, we also have to use the induction property. We write the figure first. Say we have a ball and we have a hollow conducting sphere, hollow spherical shell outside. This is the ball with minus 50 E charge, and spherical shell is also having minus 50 E charge. As this is a shell, I write the inner surface also like this. Observe now. Due to induction, inner surface becomes plus 50E, outer surface minus 50E. And already minus 50E is there on the outer surface. Therefore, net charge due to the additive property on the outer surface is minus 100E due to the additive, minus 50, minus 50. So option C is right. Observe how we are thinking of the properties of the charges to solve these problems. Now we proceed on to the next concept, Coulomb's law and principle of superposition. We learn a little bit about that, we recollect the things, and then we start solving the problem. Coulomb's law tells you the force between two charges directly proportional to product of two charges and inversely proportional to square of the distance. When you keep them in vacuum, that will give you 1 by 4 pi epsilon naught Q1 Q2 by R square. When you keep it in a medium, 1 by 4 pi epsilon naught plus the dielectric constant epsilon R to be introduced in the denominator R square. And not only this, observe, when it is in air, the force is maximum. For the same distance of separation in the medium, force is always less. That means F medium is always less compared to F air. That's the important logic what we want to remember. Say is always less than. Why less? Because always epsilon R is greater than 1. Therefore, force in medium is always less than force in air for the given system of charges and for given distance between them. With this idea, whenever there are more than two charges, we have to apply the principle of superposition. What do you mean by principle of superposition? When there are many charges like this Q1, Q2, Q3, say at point P, the net force on some Q4 with minus sign or plus sign, say, is according to the principle of superposition, is just the vectorial sum of the forces between them. Observe this A, B, C, we call them Q1 at A, Q4 at P minus Q4 attract each other. So net force on minus Q4 due to A, that's why I write FPA, is towards A. And Q2 is positive and minus Q4 is there again. This is also attractive towards Q2 and it is FPB we call. And FPC, observe, say Q4 is negative, QC is negative. So line joining those two, on that line joining P and C, it shows the repulsion. We call this as FPC. So if you want to get the net resultant force here, we have to take the vector sum of all these things, and that is done using the resolution when more than two forces are there or only two forces are there. You can make use of the resultant calculation R equals root of A square plus B square plus 2AB cos theta. This is not mandatory. You can also use resolution again, and direction is given by tan alpha equals B sin theta by A plus B cos theta. This formula when two forces are taken. But once you have many forces, you can resolve the component force into components and then add all the x components and all y components. If z is also there, add all z components. You will get net x component as x, net y component as y, net z component as z. Then take the resultant as x square plus y square plus z square. Usually we do only for two variables, x square plus y square will do. With this, now, once we learn how to apply the principle of superposition, we try to solve few examples now as MCQs. We read the first thing. An electron is moving around the nucleus of a hydrogen atom in a circular orbit of radius r. The Coulomb force between the two is, say, hydrogen atom nucleus contains only one proton and only one electron is there surrounding that. Therefore, we write one proton with charge plus E, one electron which is going around with charge minus E, like this. And we take the distance between them as r. What is the force between them? Say we call one another charge electron as Q2. Therefore, if we apply the Coulomb's law, instead of 1 by force naught, we write the constant. So force equals K. We write the vector there. K. Q1 Q2 E into E by R square. To be written. But observe, it is a vector. I have to write the sign, the direction as it is given in the four options. How to write the direction? We simply write R cap there. R cap is in the direction of F. Observe, we have not taken the minus sign. That's not required. Therefore, because we are writing the magnitude as KEE by R square, which amounts to be E square by R square, R cap gives the direction of force F. Say here it is attractive. Once you take it on the electron, it is towards the nucleus. Once you take it on proton, it is towards the electron. So, the R cap denotes the force direction. No need to add minus sign there. Therefore, option A is right. But at the same time, if you write the full vector for R, that is instead of unit vector, you can write F as K E square by R cube into R. So, when you write the full vector, one magnitude is added in the multiplied in the numerator, so one magnitude to be divided. That's why r square becomes r cube. So option B is also right in this situation. And observe all these numericals what I choiced in today's session. They are from mainly from medical exams and also some JEE mains exams and also from our CET. And one or two may be repeated from our previous sessions, but almost all out of 20 are afresh and they are not actually repeated. Now we go for fourth question there. We read, two equal metal balls are charged 10 and minus 20 units of electricity. Then they are brought in contact with each other, then again separated to original distance. The ratio of magnitudes of force between two balls before and after. Observe here in this numerical, we have to use additive property, and then we have to use redistribution of the charges, conservation property, and finally Coulomb's law. All the three things to be used, this type of things to be learnt. Most probably this numerical, this MCQ might have been repeated in one of the previous actually MCQ sessions. Now we go for it. Two equal metal spheres charged to 10 and 20. I write Q1 as 10, Q2 as minus 20 before connecting them. Then they are brought in contact with each other and then again separated to original distance. Say this sentence will tell us to calculate the new charge on the spheres. For new charge, first we calculate the total charge. Say Q1 plus Q2 is 10 minus 20 minus 10 is the new charge on total charge on two spheres because of the additive property. Then, as they are equal metal balls, the charge should be equally distributed. After separation, Q1 dash equals Q2 dash, which is minus 5 units. So now the charges are minus 5 on both. After that, after so much of things, now we read the next sentence. The ratio of magnitudes of force between two balls before and after. Observe, they again separated to original distance. That means we need not bother about the original distance. We know force is proportional to Q1, Q2. Force before is FB. Force after is proportional to Q1 dash, Q2 dash. Therefore, we are asked to calculate the ratios of before and after. We write FB by FA, which is equal to proportionality constant is removed, Q1 Q2 product by Q1 dash by Q2 dash product. Q1 Q2 product is 10 into minus 20. Q1 dash Q2 dash product is minus 5 into minus 5. That amounts to be minus 200 plus 25. That means minus 8 is to 1. Therefore, neglecting the negative sign there, we can write the answer as 8 is to 1. Option A is correct. Observe, when we want to answer MCQs, one has to think of all these aspects. But this should be done very quickly in the exam because you will get only 1 minute time in the CET. That is possible only when you practice very well these questions and these concepts. Only when you have these concepts in your mind, straight away you can apply like this what we said. And remember, in the exam you need not write all these things. You can do all these things in the mind. You can say Q1 dash, Q2 dash minus 5 each and go for these calculations. Directly you can say by doing mind calculations or mental calculations, 8 is to 1. But here for sake of explaining to you, I am giving you these details. Say we go for next question there. We read. It's again regarding the Coulomb's law only. And observe in this chapter especially, electrostatics and capacitors. We used to get 6 to 7 or 8 questions every year. So almost say more than 60 questions are there, more than 1/12, say 1/5 of the thing, because more than 8 to 9 questions are there every year. That's why we must concentrate on them again. We read, four positive point charges of same magnitude q are placed at four corners of a rigid square frame of side L, like this. It is given. It's given as square, but figure is somewhat distorted. The plane of the frame is perpendicular to z axis. If the negative point charge is placed at a distance z away from the above, then say it is also given in the bracket z is much smaller. Observe, in this situation, the Newton Coulomb's law concept is to be applied. In fact, the figure to be rewritten because it's not clear there. They have given four positive point charges of same magnitude are placed four corners of a rigid square frame like this. Say these are the four charges, each of them are q there. As shown in the figure, the plane of the frames is perpendicular to z axis. So this is the z axis as it is given. That's not clear here. Then if a negative charge is placed at a distance z, say at this point we take this distance is z from origin coincides with the center of this frame, then away from distance z away from the above frame, z is much smaller than, then which is correct? Observe, we imagine this point P on the z axis, which has negative charge, is pulled by four charges which are at the frame of the vertices of the frame like this. As they are pulling the charge downwards uniformly and symmetrically, the net force acts down on the z axis, so q start coming down. So we are applying principle of superposition here. This sort of actually conceptual synchronization with the problem solving is very important. Now, as the net force is down, because all of them are symmetrically placed, though all the four charges, and all the four charges are at same distance from the point P, as point P lies on the line passing through the center and it is the z axis. So that tells us clearly the net force is downward and it is towards the center of the frame. As the charge is attracted, as it comes towards the center of the frame, it gets accelerated because of the net downward force given here. Once it is accelerated, its velocity goes on increasing. Once it reaches the center of the frame, because of its velocity, kinetic energy, it tries to move itself on the opposite direction, and it goes on, or it continues on the opposite direction, on the negative z direction, till its kinetic energy is completely utilized and it started getting pulled back, and it stops and pulling back towards center. So it goes on happening, that means charge oscillates. So this is the overall situation given in this. Now we read the questions there. Negative charge oscillates along the z axis. That is true. We read all the three more. It moves away from the frame. No, it's not correct. It moves slowly towards the frame and stays in the plane of the frame. That's also not correct. It cannot stay because it acquired sufficient kinetic energy to move on to other side. So it passes through the frame only once. That's also not correct. It has to come back because on the other side, say here in this figure downward, it is going to be pulled back again. Therefore, the negative charge oscillates. Option A is right. But not only that, it can be made more tricky at level 3 question by asking whether this is an SHM or not. For that, we need to prove net force. In one of the previous classes, we also did that. Net force proportional to Z minus Z. If that is the case, then this is SHM, otherwise non-SHM oscillation. But here, For the CET case, it is oscillation only. Now we think of the next question there. Again, very special question where we use principle of superposition along with the mathematics idea. We read it now. An infinite number of charges, each of charge 1 microcoulomb, are placed on x-axis with coordinates x equals 1, 2, 4, 8 up to infinity. If a charge of 1 coulomb is kept at the origin, what is the net force? There is something wrong. We remove that. What is the net force acting on 1 coulomb charge? Say we write the figure first and then we learn how to solve this. Say this is the x equals 0, the origin, and we mark the points there 1, 2, 4. I am not marking it like scale, but we are marking the distance x equals, x equals, x equals like this. And as they have said, infinite number of charges are placed 1 microcoulomb at these points. Say 1 micro, 1 micro, 1 micro, 1 micro up to infinity. Now, what is the net force acting on 1 coulomb placed at x equals 0, the origin? For that, we write the Coulomb's law, principle of superposition, without worrying about the direction, because all the direction as they are positive, it is towards the negative x direction. As in the option, directions is immaterial, we don't bother about the direction. We write. For all those things, k, the 1 by 4 pi is not constant, is same, we take it out. Q, 1 coulomb, 1 microcoulomb, that's also constant. We can also write that k into 10 raised to minus 6 taken out, and 1 by q1, q2 written, 1 into 1 micro, and the distance square, 1 by 1 square plus 1 by 2 square plus 1 by 4 square, it goes up to infinity. Observe, now we write k 10 raised to minus 6, and k can be written as 9 into 10 raised to 9, as we know for air. And here observe 1 by 1 plus 1 by 4, 1 by 16. Next term if we write 1 by 64, it goes up to infinity. Observe, this is a geometric progression. Sum to infinity. We know for geometric progression, sum to infinity. Observe, that's why I said you require to learn mathematics here to solve this problem. 1 by 4, 1 by 16, 1 by 64 is a geometric progression with the common ratio 1 by 4. Say 1 by 4 by 1 is 1 by 4, 1 by 16 by 1 by 4 is 1 by 4, 1 by 64 by 1 by 16 is 1 by 4, like that. Therefore, the common ratio is 1. When we sum geometrical progression to infinity, we have the formula for summation as a into 1 minus 1 by r, summation, where a is the first term, we substitute 1 by 1 minus 1 by 4, 1 minus 1 by 4. Therefore, this series will give us 4 by 3, 4 by 3. We substitute that back to there now. F equals 9 into 10 raised to 3 into 4 by 3. Observe, we cancel 3 threes up. So 4 into 3 is 12. 1000 is there, so 12,000 Newton. Option B is right. Also, we require to learn mathematics also for solving this type of numericals. Now we go for next question there. 7th one. It is still in Coulomb's law. Next 8th question will change. It's regarding electric field and other things. But now we learn this 7th question there. Two particles of equal mass m and charge q are placed at distance 16 centimeter. They do not experience any force. The value of q by m is, say here, two particles of equal mass, say I take m and m here. They have same charge also, and they are separated by 16 centimeter, they do not experience any force. That means to say, the gravitational attraction on each mass is cancelled by electrostatic repulsion by each charge. That means, say, gravitational attraction on this charge is towards this charge and electrostatic repulsion this way. So we write Fe stands for electrostatic force, Fg stands for gravitational force. As they have given no force acts, that means these two forces should be equal and opposite. On this mass also same thing valid. Therefore we write F electric equals F gravitation. F electric we can write 1 by 4 pi epsilon naught q square by r square. R is 16 centimeter square. Fg, G, m1, m2 by r square. So r is same for both, so we cancel them. As they are equal and opposite, that's why we are equating them. And we are asked to calculate q by m. We go for it now. Here identical masses means this also we can write it as m square. So we can simply write q square by m square as, observe, G 4 pi epsilon naught goes from this side. Therefore q by m equals root of 4 pi epsilon naught g. So option D is right. Now we proceed on to next concept. I will explain a little bit of the important ideas regarding the concept of electric field lines, continuous charge distribution. Later on we start solving the things there. Electric field is the region surrounding a charge where other charges get affected. That means they are acted by force. So that is the concept of electric field. And say, once we say electric field, we must say how much stronger it is and how to define electric field strength. That means strength of electric field is the next concept. That is also called as electric field intensity. Strength of electric field, I write EF for short. Strength of electric field, as you know, it is defined as force per unit charge. Force per unit charge. This is electric field intensity at a point. It is force acting on unit charge. If we place charge Q naught at some place where we want to find electric field intensity, if the force F is acting on it, then electric field intensity is given by E equals F by Q naught. Because of this only, electric field intensity unit is Newton per Coulomb. Newton per Coulomb. With this, say strength of electric field is force per unit charge. Or we can think of electric field intensity at a point is the force acting on unit positive charge placed at that point. And as electric field intensity is force on unit positive charge, principle of superposition here also valid. And one more idea. Say if there are two charges, one plus, another is also plus, then there exists a point in between them, so at some position on line joining the charges. At that point, net electric field intensity becomes zero. Such point is called as neutral point or null point. Null point. At null point or neutral point, net field is zero. But once we have plus charges or minus charges, plus or minus, that is like charges should be there at 2 points, then null point lies in between them. But once unlike charges are there, one plus and one minus, then also null point is there, but it's outside the charges, that is not between the charges, on line joining the charges, outside the charges. Where it exists, in fact, if It is nearer to the weaker charge if, say, weaker and stronger in electrostatics means not with the sign, with the charges. If I explain it now. If I take minus 2 coulomb and plus 1 coulomb, it won't mean minus 2 coulomb is weaker than 1 coulomb. Say, because of the magnitude, minus 2 coulomb is the stronger charge than 1 coulomb. That's why stronger means the value number only important, not with the sign. Therefore, once we have unlike charges, the null point usually exists nearer the weaker charge. So with this, once we know the idea of electric field, field strength and neutral points, we proceed on to next concept. I just going through quickly through the concepts what are required there for solving, and just as a way of recollecting the things and saying the synopsis in a little bit detailed manner. Say next concept is field lines. Electric field lines are sometimes lines of force also we call. What do you mean by field lines? These are the path along which unit positive charge moves or tends to move in an electric field. Once again, these are the path along which your unit positive charge moves or tends to move in an electric field. For positive charge surrounding the positive charge, field lines are going away, that is diverging. Surrounding the positive charge, field lines are diverging, because wherever you keep unit positive charge, that get repelled and start moving on this line radially outwards. That is why for positive charge, field lines are diverging from that point. And for negative charge, unit positive charges get attracted towards the charge. That's why the field lines are actually terminating at the negative charge. They are ending at the negative charge. They are converging to the negative charge. And we know the field line properties. We just quickly list them out. Field lines originate at positive charge, terminate at negative charge. Field lines are continuous unless there's some charge in this phase. That is, field lines are continuous in charge-free space. And then the field lines are crowded where the field intensity is stronger, and field lines are less crowded where the field intensity is smaller. See, these are the properties, and also some more properties. Field lines are always normal to the conducting surfaces. That means the field lines somehow indicate the direction of electric field also. Field lines, at any point on the field line, if you draw a tangent, that will give us the electric field intensity direction at that point. And also observe, the field lines need not be straight lines always, they are curved. These are the few properties and ideas regarding the field lines. Once we know the field lines properties and ideas, now we proceed on to continuous distribution of charges. That means, say, if you can count the charges, if you can mark where they are, there, that is called as discontinuous charge distribution. Till now we learned. But continuous distribution means on a wire, if the charge is continuously distributed on a conducting wire, we don't know where exactly how much charge is. That type of thing is called as continuous charge distributions. For a line of charge, we define what we call as linear charge density. As we cannot easily say how much charge is at each point, we define linear charge density, usually denoted by lambda. That is total charge on the straight wire by its length. That's why its unit is coulomb per meter. In the same manner, when we have continuous distribution of charge on the plane surfaces, we have next charge density idea, surface charge density. Surface charge density, usually denoted by Q, and it is denoted by Q by area Therefore, coulomb per meter square is the unit. And going over to next one, volumes charge density. On the volume charge density, usually denoted by rho, Q by volume, and it is Q by coulomb per meter cube is the unit. And observe, say, we can also write electric field intensity by using these charge densities, and we have to integrate to get by the given distribution of charge to get the electric field that we see in some of the examples there. But remember, charge densities are defined for uniform as the continuous charge distributions where we cannot separate them. With that, now we start solving some MCQs regarding these concepts. We start with the 8th one now. The magnitude of electric force experienced by a charged particle in an electric field given depends on, say, magnitude of electric force experienced by a charged particle in an electric field depends on, say, we know according to Coulomb's law, Q1 Q2 by R square into K, where K is 1 by 4 pi epsilon naught for free space. So now we read all the things. Depends on charge on the particle, definitely. Velocity of the particle, it is not there. So it does not depend on velocity. Direction of electric field, that's also not required. Mass of the particle, that's not there. So option 1 is right. Option A is right. Now we think of the 9th question there. We read it. 2 point charges plus 8Q and plus 2Q are located at x equals 0 and x equals L respectively. The location of point on the x-axis at which the net electric field due to these 2 point charges is 0. Just now I said it is the calculation of the null point or neutral point. We write the figure. We are given with x-axis. Say x-axis origin is this one, x equals 0. And we are placed, say, 8Q at origin. So 8Q plus is there. We call it as Q1. And at x equals L, we have another charge plus 2Q. We call it as Q2. Now, we may call it as A and B also. The location of the point on the x-axis at which the net electric field due to these 2 point charges is 0. Just now I said, while I was saying something about the concept, when 2 like charges are there, either plus or negative, the null point comes in between them. Therefore, now as positive charges are given, null point somewhere here. As I told you, it should be nearer to weaker charge. Therefore, it is nearer to B. Let us take this as x. Distance of that point where the field is 0 is as x from A, and as it is L distance totally from origin to this point, we can write this distance as L minus x. For null point, field due to B should be cancelled with field due to A. Observe how to write the field vectors, that also we learn now. We just go through it. Say to write the field vector, you have to imagine plus 1 charge at the given point and observe there is repulsion or attraction. Say plus 8Q and plus 1 here, repulsion. So I must write the repulsive field like this, EPA I call, electric field at P due to charge at A. In the same manner, B also repels, so the field due to B is EB, EPB, like this. They are equal and opposite for null point to be there. Therefore, we write EPB equals EPA. We substitute. We leave the K, the constant there. Charge. How to write the charge? It is easy. EPB. Electric field at P due to charge at B. Charge at B is 2Q. By distance, PB. PB is L minus x whole square. Here I am using the formula for electric field. KQ1 kq by r square. So on the EPA side, electric field at P due to A, K is there. At A, charge is 8q and distance AP is x square we write. So cancel all these things and 2 4s. We can simply write x by L minus x, taking the square, whole square, 8 we can write. Therefore, x by L minus x is 4. Therefore, x equals 4L minus 4x. Sorry, it is 4 here, so it is 2. Therefore, 2L, 2x, 3x equals 2L. Therefore, x equals 2L by 3. So, option B is right. Observe, in this numerical, we calculated the null point by equating the two fields at A. As I told you, the null point lies nearer to the weaker charge. It is evident from this 2L by 3. That is 2/3 of the distance. X here, and from B it is 1/3 only. Therefore, it is nearer to the weaker charge, as we said. Now we go for next question there, 10th one. We read, 3 concentric metallic shells of radius r, 2r, 3r are given charges q1, q2, q3 respectively. It is found that the surface charge densities of charges on outer surface of shells are same. Then the ratio of charges given to the shells. Observe here, we are thinking of charge densities. Here, as the spheres are given, we are asked to calculate the surface charge densities. In fact, they have given surface charge densities are same. So we are given with 3 spheres, one with radius r, another with 2r, another with 3r. And they are given with same surface charge density. The charges on each of them we mention as q1, q2, q3. Observe here, by definition of surface charge density, we can arrive at the relation. How? We write down. Say sigma, for this I can write q1 by area of the sphere 4 pi r1 square. So this surface area of the sphere. For second, sigma q2 is the charge divided by 4 pi 2r whole square. For third, sigma q3 by 4 pi 3r whole square. Therefore, we can simply write this sigma, first one is q1 by r1 square, q1 by r square. For second one, we can write q2 by, leaving all other things, proportional to q2 by 4, and this is proportional to q3 by 9 because 3r square is there, and this is proportional to q1 by r, q1 by 1. So as all of them are same there, we can write, say q1 by 1 equals q2 by 4, which is equal to q3 by 9. We want to get the relation between q1 is to q2 is to q4. We can write q1 is to q2 is 1 is to 4, and q2 by q4, q3 is 4 is to 9. Therefore, option 1 is to 4 is to 9 is right. Option C is right. So 1 is to 4, 4 is to 9. So we write here 1 is to 4 is to 9 is the correct answer. Observe here, in this numerical, we use the definition of sigma, the surface charge density, and we applied it. So we go for next question, 11th one. We read it. The number of electrons to be put on spherical conductor of radius 0.1 meter to produce an electric field of 0.036 Newton just above its surface. Observe here, it is a combination of property of the charge, the quantization of charge and electric field, all those things. We write. Say, what is that given there? We have a sphere of radius, conducting sphere of radius 0.1 meter. And just outside it, we have 0.036 Newton per coulomb. We can take, as it is given, just outside, just above its surface. We can take the distance from the center to this as radius only. Therefore, electric field on the surface of the spherical conductor can be written as 1 by 4 pi epsilon naught q charge on the sphere by r square, radius of the sphere. Now we are given with electric field 0.036. 1 by 4 epsilon naught is known. Q to be calculated. Radius is given. We substitute. 0.036 equals 9 into 10 raised to 9. Q we don't know. And then R, 0.1. I write 0.1 square there. So this can be written as 36, 10 raised to minus 3, 9, 10 raised to 9. 0.1 square is 10 raised to minus 2, coming over to numerator plus 2 into Q. So if we simplify it, 4 is there. So we go for it. Q equals then 4, 10 raised to minus 3. In the denominator, 10 raised to 11. So 4 into 10 raised to minus 14. But we are asked to calculate the number of electrons. We know Q equals N into E. Therefore, N equals Q by E. We substitute everything. N equals Q is 4 into 10 raised to minus 14. E is 1.6 10 raised to minus 19, which amounts to be, say, which will give us 1 by 4 there. So here itself, leaving all other powers and everything, we can exactly get 1 by 4 as 2.5, 0.25. You need not bother about the power. That will be 10 raised to 5 only. Therefore, option C can be choiced. So that quickness to be observed here once we start solving the thing, because it is 1 by 0.4 into 10 raised to, observe, plus 5 is there. 1 by 0.4 is 2.5. 10 raised to 0.5. That's how we get the answer. But in the exam, if you are quick, you can say, at this step only, you can take the answer. So we go for 12th question there. We read it. 3 identical point charges, as shown, are placed at vertices of an isosceles right angle triangle. Which of the numbered vectors coincides in the direction with the electric field at the midpoint M of the hypotenuse? Say, all are identical charges and they are placed at 3 vertices of the isosceles triangle like this. M is given to be midpoint. Observe here, the field due to Q, this, say if you want to call A, B, C, field due to A on this is this way. We call it as F, M, E, M, A, field due to charge at A. And then by C, it's towards this, that is EMC. Observe, the M is the midpoint, that is AM and CM distance are same. Therefore, EMA and EMC should be same. As they are equal and opposite, they cancel. And there is only the field due to B, charge at B should be there. And as M is the midpoint and it is an isosceles right angle triangle, therefore, the line from M, the midpoint M, should pass through the B, and therefore the field due to this will be along the direction joining the Q and M. Therefore, it is along 2. Option B is right. Observe here, we are not doing any big calculation, but we are using the force electric field vectors properly written. Observe these two are equal and opposite. How we decided? M is the midpoint. M is at same distance from A and as well as from C. And charges at A and C are same. Therefore, EMC magnitude is same as EMA and they are equal and opposite. Therefore, they cancel each other just like a null point. And only one force remains, one field remains, that is field due to B. And as charge at B is positive, that should create a diverging field. So it is going away from M, but on the line joining B and M. So this is the line joining B and M, it goes away. Therefore, it is along the line 2, therefore option B is right. Going for 13th question now. We read, a rod lies on x-axis with one end at the origin and the other at x tends to infinity. That means it is infinitely extended. It carries a uniform charge lambda coulomb per meter. The electric field at point x equals minus a on the axis will be. Say this is a very peculiar question and we write the diagram first and then we think of how to solve. This is our x-axis. Say this is the origin, x equals 0 and a rod lies like this. It extends up to infinity. This is, we write it as infinity. And we are asked to calculate electric field at x equals minus a, somewhere on the negative side. So how to solve this problem? And charge density on this is lambda. For this, we imagine in the beginning a small portion of this whose length is dx. Then we write the expression for electric field due to this. And we take this dx somewhere here to get the general expression. And from origin it is x, from here it is a. Therefore, now we write the Coulomb's expression for this. Say the force, fraction of the force dF is 1 by 4 pi epsilon naught. The electric field, say dE is 1 by 4 plus naught. The charge on small element dx is lambda dx because charge per unit length is lambda. So lambda dx will give us charge on this. If you want, you can write dq there. dq is lambda dx. I write it here if you want. Lambda dx. Then divided by distance from A, we can write generally A plus x whole square. So to get the electric field at A, we have to imagine the whole wire is made up of small such elements whose length is dx and charge is lambda dx. So to get the net electric field at A at x equals minus a, we have to integrate this. Integral of dE. So integral of 1 by 4 pi epsilon naught lambda dx a plus x the whole square. As a is constant there, we need not bother about them. If we have to say write the limits as it varies from 0 to say infinity to 0. Infinity to 0. Or we can write 0 to infinity, nothing to worry. Then this will give us the final answer as lambda by 4 pi epsilon naught a only after integration. But observe, here I cap minus I cap are given. How to know that? Observe, these are all positively charged. The electric field due to this is always directed in the negative direction. That's why we must write minus I cap. Therefore, option lambda by 4 pi epsilon naught a into minus I cap is right. Option A is right. Observe how we utilize the idea of linear charge distribution here and how we integrated this. We proceed on to next question, 14th one. Say here regarding the flux electric field lines we solve this. instead of flux. Say we read, the figure below shows the electric field lines due to positive charges. The magnitudes EA, EB and EC of the electric fields at points A, B and C respectively are related. Say here we need to use the concept of field strength and the number of field lines. We said field lines are crowded where the field strength is larger. Field lines are less crowded where the field is weak. We use the idea of crowding the field lines or less crowded idea. Say here observe at A, two field lines are nearer. At B, no field lines surrounding that, only below that there. And at C, in the surrounding region compared to A and B, no field lines are there. That means at A, field lines are crowded compared to B. And compared to B, field lines are not there at C. Therefore, according to our idea, EA must be larger than EB because compared to B, at surrounding A, field lines are more. Therefore, EB. And compared to B, at C, field lines are still less. Therefore, EC. So, EA greater than EB greater than EC. So, option A is right. Observe how we analyze this situation. We solved this type of numericals, different numericals in previous sessions also. We proceed on to next question. Say, consider an electric field E equals E naught x cap, that means along the x-axis, where E naught is a constant, the flux through shaded area as shown in the figure. Observe, here it is a three-dimensional figure. X is this way, the out of the paper, and this Y is like this, Z is like this. Now they are giving us a parallelogram like this, whose vertex are A comma A, that means it is in the XZ plane like this here also. Therefore, this plane as the vertex are at A like that, that makes a 45-degree with the field direction. As field is like this, so we can simply write the plane and field like this. This is the field direction and this is the thing, and it's normal what represents the area vector makes angle 45 because all the vertex are equal and like that. So once you know these things, to calculate flux we have to calculate E dot ds. E is E naught x cap dot ds is area square, all the sides are A, so A square into ds unit vector. So E naught A square cos 45 we can write. Therefore, E naught A square cos 45 is 1 by root 2. This is the net flux through this. Therefore, option D is right. Observe how we use the component idea also or dot product idea here. So we proceed on to next question, 16th one. We read, the electrostatic field, spelling is wrong there, due to a charged conductor just outside the conductor. We read all the four options. We know electric field is always normal to the conducting surface outside and inside it is zero. We read on that concept this problem is created. We read 0 and parallel to the surface at every point inside the conductor. So it's wrong. 0 and is normal to the surface at every point inside the conductor. Both A and B are wrong because inside the conductor field is 0 completely. C. Parallel to surface at every point and 0 inside the conductor. 0 inside conductor is right, but parallel to surface is wrong, so it is also wrong. We read 4th. Normal to the surface at every point and 0 inside. This is correct one from our discussions on concepts. So we proceed on to 17th question. Here onwards, we think of Gauss law. Remaining 4 questions, we think of Gauss law. Shown below is a distribution of charges in the figure. The flux of electric field due to this charge through the surface is. The flux of electric field due to these charges through the surface. Observe, this plus q is outside, this plus q and minus q are inside. And as we know from Gauss law, let me tell you the conceptual way of Gauss law. Gauss law states that the total electric flux through a closed surface is equal to 1 by epsilon naught times the net charge enclosed inside. And also, we just discuss some of the aspects and then we'll come back to this numerical. Gauss law is valid for closed surfaces only. Closed means there's no opening. One cannot, say, touch both sides of the surface. That means it is a closed. Say, example, a water bottle with a cap. That's a closed surface. A balloon, inflated balloon with the opening is tied. It's a closed surface. Gauss law is valid only for such closed surfaces. And why it is inside only, charges taken inside only for calculating the flux? Because outside charges, say, let me explain it. Once we take a closed surface like this, once charges are outside, say positive charge, field lines are emanating from positive charge, they pass through closed surface like this. Observe, as many field lines entering the closed surface, so many leaving. So net flux is 0. That's why Gauss said to consider only inside charges. That too, net charge, algebraic sum to be taken. Therefore, the idea is, according to Gauss law, net electric flux through the closed surface is 1 by epsilon naught times the net charge enclosed. By using this, one can calculate the electric field intensity, as you know, for line of charge with charge density lambda. It is given by electric field at any point is normal to the electric line of charge, and this is the line of charge, and its value is given by 1 by 4 pi epsilon naught lambda by, or else 1 by 2 pi epsilon naught lambda by r, where r is the distance from that point. In the same manner, for infinite sheet of charge with charge density sigma, the electric field is given by sigma by 2 epsilon naught, where sigma is surface charge density. For volume charge, we have not calculated, there's no need to bother. These two are very important formulae in this electric field due to continuous distribution of charges and Gauss law applications. Now with these things, we start proceeding on to this question there. Observe carefully. According to Gauss law, we read the problem again. Shown below is the distribution of charges, the figure shown. The flux of electric field due to these charges through the surface is 3q by epsilon naught. Say, we look at the figure. Plus q and minus q are inside this surface, plus one more plus q outside. Just now we discussed, according to Gauss law, electric flux is 1 by epsilon naught times net charge enclosed. Here, net charge enclosed means plus q and minus q, which is 0, additive property used, and this plus q won't contribute because the flux from this, as many lines enter, so many lines come out. Therefore, net flux is 0. Option B is right. So we go for 18th one. It is not convenient to use a spherical Gaussian surface to find electric field due to electric dipole using the Gauss theorem because say, once we want to apply the Gauss law to make our life comfortable, we must choose an imaginary surface, what we call as Gaussian surface, by keeping in mind these things. Say, electric field on the Gaussian surface must be perpendicular to surface, one criteria, or electric field lines must be parallel to surface. Second criteria. Once these ideas are taken and we choose proper Gaussian surface, then only we can solve the problem easily. Therefore, choosing the Gaussian surface is very important, what you have observed in the derivations on Gauss law. Now we read all the four options. Gauss law fails in this case. So it is not like that. Gauss law is there. But second option, the problems does not have spherical symmetry. This is right. We cannot choose Gaussian surface as sphere because the net charge enclosed inside it is 0 and flux is 0. Electric field cannot be calculated. Therefore, option B is right. We read option C and D also. Coulomb's law is more fundamental than Gauss law. That's not like that. Fourth option, spherical Gaussian surface will alter the dipole moment. That will not. Therefore, option B is right. Now we think of 19th question. Electric charge is uniformly distributed along a long straight wire of radius 1 millimeter. The charge per centimeter length of the wire is q coulomb. Another cylindrical surface of radius 50 centimeter and length 1 meter symmetrically encloses the wire as shown in the figure. The total electric flux through the cylindrical surface. So through this surface cylinder flux is to be calculated. We know flux equals, as the wire is infinite wire, say electric charge is distributed along a long straight wire, so we can take it as infinite. We can write phi equals 1 by epsilon naught times charge enclosed according to Gauss law. What is charge enclosed inside this? The length of this wire is 1 meter and lambda we can calculate. Say it is given. The charge per centimeter, lambda, is given to be Q here. It is charge per centimeter. So to calculate it into meter, charge by centimeter means 10 raised to minus 2 meter. Therefore, 100 Q, because 10 raised to minus 2 goes to numerator, means 100, it becomes charge per meter. Once we know lambda, we calculate charge enclosed. So phi equals 1 by epsilon naught. Charge enclosed is the Q we know. So lambda, that is Q, the charge per thing is given 100 Q, and the distance length is 1 meter. Therefore, net charge enclosed is 100 Q into 1 meter. Therefore, 100 Q by epsilon naught. Option B is right. So observe how we are using the Gauss theorem. The last question for this session referred to the arrangement of the charges in the figure. A Gaussian surface of radius r with q at center. Then say this is the Gaussian sphere, phi q is outside, minus 2q inside, and q is at the center. We read all the options. Total flux through the surface of sphere is minus q by epsilon naught. According to Gauss law, external charge need not be considered, only charges inside algebraically added and to be considered. Minus 2q and plus q is there, minus q. So this option is right. But this is multiple option question. We read other options also. We just check. The field on the surface of sphere is minus q by 4 pi epsilon naught r square. Field on the surface of the sphere, Gaussian sphere, it is minus q by 4 pi epsilon naught r square. No, it is not correct, because to calculate the field phi q effect is also to be taken. Therefore, B is not correct. C, flux through the surface of sphere due to phi q is 0, as it is correct. As we said, phi q is outside. C is also correct. We read D. Field on surface of sphere due to minus 2q is same everywhere. It is also wrong, because minus 2q is not at the center, it is at some point. Therefore, D is not correct. For this, option A and C correct. So, in this session, I have talked to you about concepts and how to apply the concepts. Instead of giving you synopsis in the beginning and then going for solving the numericals, as I did in the previous cases, I told you the basic ideas there itself. But in this session, I did it elaborately. Therefore, you just go through this class very clearly. We continue with this type of things in the next coming sessions. There I conclude.